Greetings, everyone. We are group number 5, and today we're going to be showing you the design and simulation of a centrifugal pump. Our agenda for today consists in introduction, geometry, mesh independence, physics involved, results and analysis, and conclusions. For starters, the objective of this project was to apply mathematical models to design and simulate a centrifugal pump whose parts consist in an impeller and a volute, using different software such as Excel, StarCCM, and Inventor. Also explaining and analyzing the results of efficiency curve and determining the best efficiency point flow rate. But what exactly is a centrifugal pump? Centrifugal pumps are turbo machines used in different industries such as food and pharmaceutics for their great utility in the transport of fluids. The main way to displace the fluids is to transfer energy due to an increase in pressure. This equipment is essential in various industrial processes as it models behavior and performance under different operating conditions.
Now for the literature review, we're going to check the state of art by reviewing some vital concepts to understand this presentation. Basically, we did a CFD simulation that tries to predict the behavior of a fluid that is increasing its pressure using a pump. We made a mesh that is made with small cells, which conditions we will check later on the presentation. On the other side, when we choose the pump conditions, we have to take care of not generating cavitation because this may damage the pump.
Now, for this project, it's also important to know what is CFD. CFD stands for Computational Fluid Dynamics. There are nonlinear conservation equations for mass, energy, and momentum that are fundamental to model systems. However, it's not possible to solve these problems analytically. This is when CFD becomes the topic of the conversation. In terms of the tools we used, the meshing was one of the most important ones. It was developed with a volumetric extrusion in the inlet and outlet in order to obtain a fully developed flow and an accurate constant velocity profile. As for the type of mesh that was used, three different types of polyhedric mesh were found useful for the design. Then, a thin mesh was selected to work with, as it ensured the transition of growing cells up to 30%.
And now I will show the main information of the pump that you will see in this presentation. And now for the liquids parameters, we have the densities and viscosities of both water and oil. We also have the rotational velocity that is the same for both. We can calculate with all these numbers the Reynolds number with the formula that we have here, that it's with density, viscosity, the diameter of the inlet of the pump, and the rotational velocity. And we got results of around 28.7 million in water and 700K in the oil. And then in the renal analysis of the regime of these two liquids, we got that they are in the turbulent regime because they are way ahead of 100K. And for the turbulence model, we used K epsilon because this model allows us to run simulations in high Reynolds liquids, and also it has a low computational cost. And now we have the three essential parts of the pump. First, we have the housing, that it's a critical component that encloses all the parts and provides structural integrity to all the pump. Then we have the impeller, that it's the main rotating part that will imprint rotational velocity to the fluid. And at the last, we have the diffuser, that its main purpose is to slow down the high-speed fluid that comes charged from the impeller. The mesh assumptions. First, we have chosen polyhedral measure that requires less cells than tetrahedral mesh because it has more phases and it can do the same results in less cells. We also have chosen the surface measure that require more cells, specifically in the curved surfaces. We also have the thin measure that require more cells in the thin areas, and the prism layer measure that require more cells in the areas that are near walls.
Regarding the meshing, three types were obtained, differing the number of cells. A base mesh was created to which some parameters were modified, such as the base size to obtain a coarse one and a thinner one. From this, MSE was calculated regarding the head and the manufacturer's efficiency, as well as the computational time to obtain these meshes was graphed. For the selection process, it was considered that in the head figure, the mesh with the lowest MSE was the base. However, when taking into account the efficiency, uh, the coarse mesh had a lower MSE. Nevertheless, in both cases, the difference between the one with the lowest MSE and the fine one was small, 0.64% and 21% for the head and efficiency, respectively. So this mesh was preferred since it generated more consistent results. Likewise, this number of cells is relevant for designing pumps in with turbulent flow. On the other hand, the head versus the flow rate figure for water and oil was obtained, both through simulations and from the manufacturer. In this, it was observed, as expected, that the curve is smaller due to possible losses. Likewise, the curve of the mineral oil is smaller due to various factors such as its viscosity, which generates greater friction losses. In addition, a behavior of the curves generated by CFD can be observed, so it was decided to calculate the dimensionless specific speed. With this, it was observed that it was still within the radial flow range. However, the behavior evidence is similar to that of a mixed flow rate. In analyzing the efficiency versus the flow rate graph, it can be observed that oil efficiency curve is lower than the water one. As mentioned before, this is due to the increase in friction losses due to the increase in viscosity. As for the efficiency of the CFD water with respect to the experimental data, it may be due to the decrease of decoupling power. To compare the values of the head and efficiency obtained by the simulations with those of the manufacturer, the graphs in figures 5 and 6 were made. In the first place, it was not possible to add the bed point calculated by the simulations because the value was higher than the free delivery of the manufacturer, which is the last operating point, which does not allow comparison beyond this. For this reason, the values were looked at a flow rate of 0, 90, 182, and 210 cubic meters per hour. In figure 5, 3 out of 4 points were within the limit of a 10% error, which tells us there was a good approximation between these ones. The same occurs with figure 6. However, in this figure, the value that is outside of the deviation range is quite close to the limit.
As expected, the velocity profile for both oil and water is the same for the different flow rates because the velocity is kept constant for all simulations. It can be observed that the inlet flow rate increases, the velocity in the impeller decreases. This is due to the fact that more friction is generated between the fluid and the impeller. Likewise, in the bullet, this velocity increases and the amount of fluid passing through this region increases. Additionally, the increase of the rotational speed is higher for water compared to oil, which can be explained by the fact that oil has a higher viscosity. Regarding the wall Y plus, it is a measurement that provides information about the resolution of the boundary layers and the influence of viscosity in the vicinity of the wall, where the fluid moves slower due to the friction with a solid surface. In Table 6, it can be observed that mineral oil has a lower value of wall weight plus in every flow rate than water. This is due to the higher viscosity of the oil. This viscosity causes a smoother velocity profile near the walls, which reduces the friction velocity and at the same time increases energy dissipation in the boundary layer. In Table 7, it can be observed that the areas where the greatest cavitation occurs are in the suction zone at the tip of the plates. Moreover, as the flow rate in the centrifugal pump increases, the velocity of the fluid through the impeller increases, resulting in the greater pressure drop of the pump inlet suction pipe. If this pressure falls below the vapor pressure of the liquid, cavitation occurs. This pressure is 2,300 pascals for water and 1.6 pascal for mineral oil at 20 Celsius. The following animation shows the movement of the fluid in the impeller. In both cases, it can be seen that the impeller blades are tilted backwards.
To finish, we can say that we recognize the physical models that rule the operation of a centrifugal pump, constructed its geometry, and imported it into different programs of CFD, realized several simulations, constructed an operation curve, and compared it to a manufacturer's to see if they were appropriate. In these results, we could see that water has a better efficiency than mineral oil. The water pump simulation has a lower efficiency than the manufacturer, which is expected. The simulation can be carried out again in order to evaluate the behavior of different type of fluids. Adding more blades can contribute to provide a wider attack angle, reducing cavitation and avoiding black flow zones. The objective of this project was reached, designing a functional centrifugal pump, and the wall-wide class is mostly affected by the viscosity of the fluid.